Okay, without much ado, welcome to day 1, 2, 3, 4, 5. Yeah, today is fifth day of these sessions. Um, let quick one. Can you hear me? Do you have any questions from the previous or previous discussions that we had in the last few days? Please ask. I'll give a few seconds and start immediately. Okay, like that you can hear me well and good. Others, start. Uh, 2015 training manual, but the lessons have been reorganized a little bit. You will be able to see it. As I told you in the previous session, if I'm coming to you or if I'm meeting you, please keep me posted. I have ordered a few training manuals from my end. I can help you out with the 2015 training manuals on simulation. So the topic today, and rather today we are trying to finish the simulation professional training manual, which you should, I believe, I have discussed most of the topics in simulation and simulation professional, moreover on the technical front, that is on the domain front. I believe you should have done the exercises on your own, or you'll spend some more time to do it. So let this be a continuous process. You will know my contacts. You can contact me in future as well. But coming to today's point, we are going to discuss today the stress analysis. I may not advanced, but yeah, thermal stress analysis and tool simplification. A bit a little concept in terms of how we can actually represent a geometry in the form of this going. Okay. So first of all, 2D simplification. Typically, as of now, we have only discussed or understood the concept of axis or not axis symmetry. How should I say, the cyclic symmetry and symmetry. I believe that those two simplification modes or optimization modes are clear to you. We also discussed on first day that typically for simulation, it is always advisable to idealize the geometry. We cannot go ahead with the geometry as it is. Okay. So today we'll see a few more options by which you can simplify the geometry. They are no simplifications in the software. One is axis symmetry, which is going to be used while do the analysis work here, and the other are more towards this. One of them is called as plane stress. The second one is more of plane strain. And again, if I put it simply, or if I think in terms of plain language or just a general purpose language, really any long structures, infinitely long, something like this, or take a few standard examples, say a huge dam which is have a comparatively longer length compared to its cross section. I would say meant something like weldments which are represented as beams. Those, if they are to be simulated in the form of a part only and the consistent cross section, then we can actually use plane strain elements. On the other hand, if we don't expect too much things to be happening across the thickness, I like elements which are bending as well, and they are comparatively, I would say, uniform in thickness, and the stresses are expected to be in the planar direction only. That we also have these elements called as plane stress elements. Now, the examples of this could be, there are many examples of this because many thin parts can be represented in this form. And if I remember rightly, one of the questions which I get, and standard question, is of that of a bushing which has been used in the exam, and we are asked to use plane stress elements over there. These are the three idealizations that are happening. Axis symmetry is the one that we are going to use today. Typically, such circle or those which have constant cross section in the circular direction, they can be presented by using such a cross sectional entity only, and the simulation can be actually done on the entire setup or cylindrical part. One point to remember, it is not only the geometry, but even the loading and boundary conditions should be symmetric. If not, it goes haywire. Here, the loads are in a format only. They cannot be random or ununiform. For if I take this particular cylinder and I draw it in a different way, I expect 10 applied here and expect 10-20 Newton to be applied on the other side. Okay, if this is the case, if this is the case, then obviously we cannot use axis symmetry over here. Even though the geometry is axis symmetric, but the loadings are not axis symmetric. Logic holds good for friends as well. So be cautious about that topic. So I take this example, we'll see in the software, how do we create it? I all these, I would prefer using the software itself directly. We'll see it in the software. Okay. Okay. Software. Okay. Right click, new simulation study, thermal. Okay. I believe yesterday you understood the concept of thermal analysis and the difference that it brings compared to the stress analysis. What are the difference? When we need a thermal analysis, or we need to ensure the thermal analysis before we do the stress analysis, right? So let's see. In this, I believe after we do this example, it should be more clear to all of us. So for the new concept that is coming here, which is of the axis symmetry, so very simple. For certain kind of analysis only, you will get this option of use 2D simplification. On setting it, you will get 3 options, and you can see they are directly shown over here appropriately as per the availability or as per the eligibility of this model. So symmetry, like that, you can see here the geometry is already shown. Typical for extruded, it is showing what kind of thing can be used with max. Okay, I go to symmetry. Over here, it is asking for a section plane. So typically select a plane which can be used for creating the cross section. There I need to specify the reference axis. Okay, on that you can see in the yellow sketch kind of thing, you can actually see the cross section that it is showing. It will help us understand if it is all okay. So I accept it. That's it. So we an axis symmetric model. So in terms of geometric editing, or what we need to do in terms of these things, this it is. So we are presenting it in the form of an axis symmetric model. Okay. Feel free to explore. You should be able to do it. So these two now material has been taken for SolidWorks from SolidWorks. So solid fine. I believe you guys are comfortable with it. In terms of bonded contact has been used at the global level. Again, those are detected. And if you have seen here, typically more of bonded or yesterday as we discussed, for thermal analysis, bond would mean that just that the temperatures are moving, or the heat flux is moving from one part to the another. The that have been done. It is a kind of I don't know what to say, sealant or something like that, and the temperatures have been applied on all the internal walls of this spring-like or bushing-like vessel. Have been maintained at a temperature of 220 degrees Celsius. The internal, I would say, walls of this particular entity. Thereon convection has been applied on the external walls. The heat flowing out of the system from the external walls to an ambient temperature of 298 Kelvin. Okay. Finally, yes, I think that's it. Let me check anything else that I need to highlight. It is a steady state. The direct spark solver is used. That's fine. So on solving, basic things that we see is temperature. You can see temperature plot. So what analysis has done is, based on the convection applied, the internal temperature, it is calculating the temperature distribution and inside geometry. And obviously, the other important thing for us will be the flux, or we want to see how the heat is flowing. So shows these arrows show you the direction in which the heat is flowing in this system. One part of the analysis that has been highlighted over here, but in terms of theory, we know how to create two-dimensional geometry. Yeah, by the way, in the form of results, you can actually edit this and see here the option to say show as a 3D plot. So you can visualize this in the 3D. There are options to select how much angle you want to see. It could be 180 or it could be 360. You decide on that and analyze appropriately. Analysis is thermal stress analysis. And so here is, now here, these two are not typically combined. In one we did the thermal analysis, temperature distribution is taken. This is just a normal creation. I do a static analysis. Again, I use 2D simplification. I go there, I define these details, and it all set. Okay. Going back here, yes, let me do that. So this one bonded contact, this is fine. Now other things would be what we want to understand. Let me take a standard view for this. Let's take geometry to the screen so that I can visualize it correctly. Okay. So we are first is symmetry boundary condition. So at a certain end or here, there could be two different things. This is expected to be replicated. On the side, we are taking only half the geometry. So this is being represented using the symmetry. We also have the reference geometry option or input that has been used to compress this kind of vessel or spring like a vessel by 4 millimeters. Okay, it's been pushed inside. Of loads, there is an internal pressure that has been applied, internal pressure of 0.3 megapascals. The most important thing or the new thing that you are going to see is this particular pressure. So this can be applied from multiple places. You can select the option, right click and select thermal effects, or you go to the properties and go to flow thermal effects, and you can decide which study you want to take the temperature and time step. Now this step is relevant especially if it is a transient analysis. If it is a time dependent analysis, this step is relevant. So this is what it is in terms of definition. So what is happening is, I missed out on that. One of the important things over here in terms of flow thermal effects is this thing called as reference temperature at zero strain. You can see this has been taken as 25 degrees Celsius. Okay, this is the temperature from this part. That state, it is assumed that it has zero strain. Then actually we are saying the temperature is going all the way to 220 degrees Celsius. Am I right? Let me use general units and so it's around 220 degrees Celsius. So from 25 to 2 degrees Celsius is what the temperature is in this part, and it also has a compression from one particular end, that is negative x direction, right? So those two effects together are in this thing. Typical solution happens and we get results something like this. Let me take a standard view. Let me zoom in over here. I think it would be interesting to see operation that is happening. Unfortunately, visually, I'm not able to show you the difference in terms of temperatures only. But just for curiosity, I would like to create here only and see the effect of temperature stresses only on data. Let's try to do that. So I suppress, or I go here and let me solve this suppress. Let me suppress the pressure as well. Only with symmetry and temperatures I'll solve this. Okay. what happened? Some voice came. Okay, it's doing. What it is all about thermal stress analysis. We also saw the simplification thing. Questions on these two topics. We are while this is all. It is easy thing, but I think most of us do mistake in handling thermalalysis, in handling thermal stress analysis. And it's really hard to explain at a random moment in time. On the training manual to check if anything is missed out. Um, I guess no questions on that. If not, we'll take these questions. Take question number 1. State at least 2 examples where 2D plane stress, plane strain, and axisymmetry simplification could be used. I have mentioned a few examples. Here are some examples from you. For plane strain, any example for plane strain? System, okay. So it may not be the system, but more of only if it's single long pipe as that's shown on the monitor here, then we can accept it to be plane strain example. So I would not go into other two. I think it is it should okay to you for you to understand. Let me check what is this. Okay. The figure shows a pipe loaded by uniform internal pressure. Let's take question number 2 and distributed force applied on the top edge. The force magnitude varies along the longitudinal direction of the pipe. Which the following 2D simplifications could be applied to reduce the size of the problem? So what we use here, is it plane stress, plane strain, or axisymmetric, or none? Can't be used. What is the answer? Plane, plane stress, or axisymmetric? Given these things, yeah. So you are right in the sense, if these things, the forces, you can fortunately they are not symmetric or axisymmetric in nature, applied only on a single line, and unfortunately that creates a problem. We cannot treat this geometry as a axisymmetric geometry. Okay, please keep small things in mind when we do it. Okay, let's move on. These two are exercise things which can be data. Okay, into fatigue analysis now. Uh, in the can we start off with fatigue analysis? As just yesterday, can we just recollect what are the different failure criteria that we understood as of now, or that can be simulated and understood in the SolidWorks simulation module, and at the different failure or criteria or failure that we can understand from simulation. Can list them? What are the different failure criteria? Yeah, fatigue is definitely there, which is one of the failure criteria, and we are going to discuss now. Yielding. So typically, ductile materials, when they are applied a certain load, stresses can go so high that they could be they may be crossing the yield point, and which is not what we want. And failure it can be considered as failure. There are some certain products which might be working even after yielding, but if yielding is one of the failure criteria, then yes, it is considered. We discussed about, buckling is one important thing. So as mentioned, as discussed yesterday, buckling in typical thin structure subjected to load, even at a lower force than what it might be yielding. Okay, so that is one. Two, third is fatigue, which we'll discuss now. What's the other one? Important one, resonance or vibrations, the natural frequency thing that we discussed yesterday. Okay, so there are a few important things in terms of thing, but something offhand in the sense you want to take it, but typically for brittle material it is not yielding, but it's a brittle fracture or brittle failure. Okay, and what else remains? Thermal stresses are fine. And discuss any other failures. Yeah, I think that is it. So these are ones. Now we're moving on to fatigue, and the an example of, oh, this was yet solving. I never saw that. Okay, I think to stop it. Something. Okay, let me reopen this. I want to check if I can get you some good video on in case and this should be, let me try to get this. Open the file set. Lesson 9. Case. Let me open the assignment here and the cross section. My content for presentation. Video. Not this. Okay, but I shown you these things yesterday, but in case you're curious, and this is one of the things where you can see actually a buckling failure. It's a failure wherein the internal vessel is being pumped pressure and trying to create some little imbalance in the vessel, so maintaining the eccentric and this is buckling failure. It's certainly had created a vacuum in there. Sorry, it was a vacuum. A few more. Okay. That in terms of understanding, nothing wrong in these string skipness. Okay, cannot. This random animation, no bridge challenge. I've seen this video, but a typical random vibration failure. It is for a helicopter. See that. Drag board, no. I'm looking at fatigue and I ended up showing you some different things, but yeah. This is a fatigue test wherein the shaft is being oscillated. Let's try to get something different for you. Laptop, one pound for buckling. My fatigue. Go. Okay. Okay, that's. I would like to just check if I have uploaded something here, which is to go fast to the right, and let me open fatigue. Yes, I'm down here. You can this shaft. Actually, for shafts, it appears as though they are rotating in a circular way, but in fact, at a station, the shaft will be undergoing all the way from a tensile load to a compressive load, and depends. Of course, it depends on the loading conditions. but really it can happen so. Or the example that is shown in the video, wherein it could also be a torsional thing. Other way around, this is what we introduced in 2015. We can also simulate dynamic fatigue. That is, in one or the other, what we are discussing as of now or today, or what the software had, it was more of static fatigue, wherein that was coming intuitively, but in slow and decent manner. Whereas if it could also be something like this, where it's vibrations and it is coming randomly also, and you want to understand the life of the component. As the random load, yeah, the logic is not that straightforward, and it involves a bit more involved topics. No, sorry. I have this now. So let's go to the software. Let's check out in the presentation. Also, that if I have any good content which I can use to speak. Okay, this is not frequently discussed. One of the oldest or one of the affected failures that had happened at a certain stage was in aircraft. Most of the research that happens in industries is more towards or the aerospace, because both me as well as there is huge amount of expectation as well as necessity to do the research, and I believe even fatigue was had its origins all the way over there. Typically, there was a case of failure in a aircraft wherein everything looked good, but at a certain stage it had failed, as shown in the below picture. And research it understood that actually it was the repetitive loading or the repetitive loads which the aircraft was undergoing led to such a kind of fatigue failure, which was called as fatigue, and which we are now using quite frequently is as this for life. Or their other part or the previous thing was design for strength, wherein we just see the yield strength. Okay, so we are talking more of this for life. Now the way it works, okay, the way it works. Typically, the way we have material properties for yield strength, Young's modulus, Poisson's ratio, etc. We also have one more material property called as the SN curve. What is this? It is a curve which is having one of its axis with stress, which is actually mean stress. That is when a cycle happens from a negative to positive or 0 to positive, it will have a mean stress over there. This particular stress, and if is subjected to that kind of repetitive loading, then after how many cycles will fail, that has been listed or jotted on this particular SN curve. Okay, where you can see if it is around 15 psi, then the life is around 10 raised to 6 cycles. Typically 10 6 or something above this, consider it to be infinite life. Okay, the life anything below this or stress levels below this value called as infinite life. In this number of cycles that it can withstand it more 10 raised to 6, and the stress that is coming at that level is called as endurance stress or endurance limit. Typically, it will be half of yield strength, meaning more of a rule of thumb, but it can vary, and the absolute values can be understood using this SN curve. So one way, if you observe this, if you hear what I'm saying, but actually a post-processing option, that the x of force is equal to k into m, etc. in a static analysis are more of solving. The question comes, we know the stresses from there. There in fatigue analysis, we are comparing those stresses with the kind of loading cycle, like the loading cycle is used to more understand is the mean stress, and on those stresses which are all over the body are compared with this SN curve, and we come up with the life expectation at different locations. Now, could be like, typically when we do the analysis, we are actually giving the number of cycles that we expect this part to withstand. They understand how many cycles it can withstand after, or other way around, after how many cycles it can fail, or life is remaining in the part. So a few things which come up as an output. So if you observe, fatigue axis is actually more of a post-processing option, and comparatively, if you, when you solve it, you see that it is quite fast. It is only using the stresses and comparing it with the SN curve and giving a nice plot of life. That's it. Okay, important concept which we want to understand. For different parts, okay, or different these kind of cycles, we discuss something called as low cycle fatigue, wherein part fails below 1000 cycles. That is, within 1000 cycles, there is a high priority of the part to fail. And I mentioned a few minutes back, it can also be more than 10 raised to 6. And we say this to be infinite life. That is, if the number of cycles is more than 6, we part as infinite life. And on the other hand, if it is somewhere between this, that is less than more than 10,000, more than 1,000 and less than million, then we are talking about something as high cycle fatigue. Okay, high cycle fatigue. Okay, this is called as high cycle, but it is going towards the infinite range. But this between 1,000 to 10 raised to 6 is what simulation can simulate. The interesting fact, and to understand, there are cases when we talk about failure of a part after 10 cycles of repetitive loading, 20 cycles of repetitive loading. These are cases of crack propagation, wherein crack will have already occurred in the object, and now we are simulating or we are understanding how much time the crack will take to propagate or go inside the geometry and finally lead to the failure of the geometry. So this is more low cycle fatigue, and unfortunately at this point of time we cannot simulate it in solid simulation. So be aware, our software is more towards high cycle fatigue and simulate between 1000 to 10 raised to 5 cycles. Makes like this that we are using is more suited for the range. In terms of understanding that, we need to know if there are multiple loads. Okay, there can be multiple stresses or multiple loads. Then the way it treats is what is called as Minor's rule. That is, the stresses coming from multiple loads are treated using Minor's rule, wherein if you see in one way or the other, it is simple addition. So or other way around, if we see practically, the expectation that after application of a load for a certain amount of cycles, there is an amount of damage, and thereon one more load comes up, and there is a kind of order when we have these multiple loads that are working on a shaft or any product. Whereas we are doing it using Minor's rule, the order in which these loads are applied does not have too much significance. It is that have been added. So for all practical purposes, this is accepted. This is the way it works, and it's also okay to assume it. Of weightage that is being taken here, from if you see this simply, at stress levels of S2, we expect it to withstand N1 cycles at a certain location. At stress levels of S2, it is N2 cycles, and total damage is more of using the kind of equation. Total becomes 1, it is expected to fail. Fine. Linear image rule assumptions. Okay, these are the assumptions which I mentioned now orally. Effect of load sequence. So sequences of no relevance caused by stress cycles is independent of where it occurs in the load history. So is a significant thing that we need to understand. Obviously, you not want to highlight all these things that I mentioned here in a demo case, but these relevant things that we need to understand. Ray accumulation is independent of stress levels. Okay, yeah. The used to okay. In this software, it is just an option. To treat such scenarios, we have this linear damage rule, which is of mass rule what we discussed, and there is also as ASME code there is one more method of doing it, and we can specify it to be the random events method that it helps it in a different way. But ultimately, if the customer wants, it is they know what they want to use. We are working in millions of cycles only, so that these two topics need to be understood. In terms of stresses, when we apply the loads, we have a few different options over here. One called as fully reversed stress. So typically, the stress that we are taking from a static analysis is the sigma max. Here on, we are saying it is fully reversed. That is, it is expected to go completely on the other direction. That is, if it is plus 10, this can go all the way to minus 10. Okay, minus 10 is not a static analysis which is done. It is done only for this. We are selecting this in this thing, and the mean stress is used. In one way, the mean stress for such a thing can become 0, and multiplication factor, which we'll discuss a bit later in going to software, but this is the way it looks, a fully reversed event. It could be also pulsating, or we can say it is entirely on the positive side, wherein in such case the mean stress can be equal to the amplitude, that is the maximum stress that it is going, or the how can I say, the from the level, the stress level. So this small, yeah, it's shown it here. This value is what is your mean, can be completely offset from the zero stress. That is, the results never come to a 0 level, they are always above, and again it has a different thing. Stress ratio is fine, mean stress is half, this is under note. Okay, and no big deal. Means, yeah, this is the same graph represented in a different way, especially these three graphs. Okay, I will understood from there. By the way, in this you can see it can go on the negative side also. It need not be positive. It can go on the negative side as well. And from whatever tensile and compressive loads that we discussed yesterday, especially for buck analysis, even they have a certain kind of different effect here. The tensile stresses lead to the decrease in the fertilizer, whereas compressive mean stresses is beneficial and can actually and they have negligible effect on the durability of the part. So if the part is subjected to too much compressive loading, you may not experience fatigue. Okay. Then 0. Whenever the practical calculations are done, or whenever these curves are derived, they derived at 0 mean. That is, the stress goes from positive to negative, and that cycle is continued to check the component and the life of the component. If such kind of loads are applied on a part, so as I told you, first of all, this one 0 mean stress. Okay, 0 mean stress. This comes from practical calculations. There, depending on the loading, we might have negative mean stress or a mean stress. Okay, so based on that, the curves will, from software or from the practical test, we have these kind of results. Then on the loading, the curves might offset from this mean stress, and how the offset is what is shown here. As this is expected, the red one is stress, and the life is actually lower at a certain given of stress level, Whereas if it is compressive, then life can be more as well. This is multiplication factor, which is R over here. Where did you check it out? Okay. This is something different in terms of loading. Now, this kind of loading can be either constant or the way we are seeing here, or also it can be a variable amplitude loading. Okay? It can be variable. An interesting fact would be how do we treat it if it is variable is what we need to understand. I wish I had some images to show you over here, but typically even this loading has certain kind of frequencies or amplitudes which are iterative. For example, if I take a amplitude somewhere like this, okay, something goes all the way from here to top, there can be those kind of repetitions all the way in this one, and the software has the options by which it will segregate these different frequencies. So it can happen that there are a few cases where amplitude is 5 units and frequency is 10 hertz. It will separate all kind of different amplitudes. Okay, it could be 1, it could be 2, it could be 3, and all these are added using Minor's rule to get us combined for such a kind of variable amplitude loading. So, software perspective, it is very easy. We do certain selections and it takes it. This can be given from an Excel sheet or wherever you have saved it, and finally get answer. In terms of results, we get life plot, number of cycles to cause a fatigue failure. We can understand that. Oops, sorry. We can understand damage, amount of life consumed by fatigue events, safety, how much base fatigue. So we can understand that. And biaxiality is more, I would say, in stresses it is going to show you. It is a indicator. Sometimes if it is too huge, then we expect failures to happen, and that kind of plot can also be understood. This okay, the stresses can be from both. That is, it can be both, wherein it can be structural as well as thermal. And secondly, one interesting topic which I will try to cover, but it is more towards dead. So even if a load in a repetitive manner, in most of the analysis there will be at least a few different things, or it is as simple as the press created by a bolt. Okay, this press is not changing, or it remains constant throughout, and it is called as a dead load. That add to the overall stress or the amplitude of the stress, but not in a repetitive manner, but it is just offsetting the stress level. And there are examples in this setup by which you can understand how to simulate that. Okay. So let's go to the software. Let me a bit more. This was a useful thing. Let me discuss this particular part. So this curve discuss more of a random fatigue load, random curve that is going to come into picture, and this image. Let's just a second. Okay. Of things. Let me go back. Okay. But if I give a overall perspective here, and actually most of us will not have these parameters. Just for understanding, we are discussing here. Typically, as we discussed, the fatigue failure happens because of a crack that might be coming somewhere in the object. Okay. Now we are discussing obviously a cycle fatigue, which is not because of localized cracks, but it is more of material deterioration over a period of time, and we are comparing with SN curves to get it. But that even the SN curve, typically they are derived from a standard specimen. So specimen has good surface finish. It has a certain kind of corrosion. like or zero corrosion, the size is decided. Like when the size of the component goes up, typically the manufacturing details change and it can lead to different kind of fatigue. There is also factors like notch factor or other things. Typically, when they do the practical testing, the temperature loading kind of thing may not be there. There might be vibrations. So all such n number of different the different factors are there, which actually accounted by only one simple which is called as fatigue strength reduction factor. So the fatigue analysis, that factor is going to reduce or tell the software that yes, you can depending on the geometry, this is what we need to understand and we need to opt for in terms of results. Okay, so these things have been in one way or the other discussed here. There is something called as corrosion factor. We can discuss these things in more detail in terms of each of these things, but ultimately when we go back, we have only one option, which is fatigue strength reduction factor. Most of us don't take actual values for all these things, corrosion, or surface finish, size effect. So the spin may be of a certain size, but when the size goes up, there are possibilities of failure in a different way. Loading, how it is, whether it is axial, bending, or those things can also lead to failure, because when we do the test, it is under a standard condition. It could be temperatures, high temperatures or a different set of temperatures can lead to a different SN curve. Low temperatures, yes. Reliability factors, those also come into picture. More statistics, but yes, they can cause difference. Niche effects. So if there are different places where there is a notch in the design, then that can cause failure. Fretting effect, or what's shown in the images over here. And yes, so huge number of factors, but unfortunately, for our good, when it comes to the software, we actually have only one input that we are giving, that is this thing. Second, in terms of infinite life, we are talking about 1 million cycles. If you have observed, if the stress levels are too low, sometimes the results that come from fatigue analysis are meaningless. Many do not understand it and they creep. But the fact is this value as well. We are specifying that if the stress is below a certain value, there is no point in showing results. It is actually infinite life. Second, first, or one of the important things which we discussed before, wherein if it is a random load, is there an image? Yeah. If the load like this, if there is load like this, as I told you, that will be segregated. Let me clear it. Dirty this screen. Pointer options, erase all. Okay. This option, where is variable amplitude events, those are filtered out using this one. Now, number of bins is telling the software on how many different sizes of frequencies to take. So it first of all filter out, then it will put them into different bins kind of thing, and thereon it can neglect filter cycles below 1% of maximum range. So we see a maximum range, and it might understand if it is 1%, there could some noise in that particular curve. All those factors are neglected. So this of a how can I say, the segregate or understand or get some meaning out of a random curve, which is something like this. Okay. Other options are here, computing alternating stresses. So as I told you, the SN curve is actually comparing the alternating stress versus the mean number of cycles. So the alternating stress has to be calculated to compare the software, and for that the point is which particular alternating or which stress has to be used for calculating the alternating stress. Now it can be anything. It can be principal stresses, which is intensity can be used. It could be von Mises. We discussed a lot on von Mises. It can that direction, or it could also be maximum absolute principal. So he's only taking one value and sticking to principal stress. Stresses, as I discussed, depending on whether zero, tensile, or it could be, it could, and um, we may not understand. Um, in this, I will say it can be a different place, and we not. How can I say? To effect the effect of a tensile load, effect of a compressive load on the life. Then there are few different theories which help in treating it in a certain way, and these are the three theories that one be none, that is we're using the curve given by us as it is, no much things thought. And if you want them to be treated, frankly, I'm not going into those three theories, but those three options will be available. If you are interested, I can show you where we have a bit of text on those through theories. We can definitely check it. Good, we can go through this, but frankly, hard to use them in the software, understand as well. If you explain and tell the customer these things, they will not have any content to give on this topic. This rain flow matrix. Okay, let me now go back to the software. Let me close this and okay. Okay, let's see how it looks. So this is a case wherein a thermal analysis has been done. So now you all are experts in thermal analysis. You know the way done is a heat flux applied on certain walls internally. Let me show you that. Okay, internally. Okay, then we also have convections on the external walls and the temperature distribution. Next, this pressure vessel. Okay, this is a pressure vessel. So maybe if you are doing pressure vessel analysis, this could be the process, or these could be things that are required. The analysis, wherein taking the temperatures from thermal analysis and doing thermal analysis. While it does all through this training manual. Guys, questions as of now, please ask. These are kind of big topics, that is yesterday thermal, today fatigue, very relevant and important topic. Okay, analysis is done. Let me reapplied. Yeah, certain amount of force is also given here at the top. Thermal loads are coming from the thermal analysis. So this is all good. This analysis done. When is a case where we are also showing how to do load analysis. Okay, so that sense, even that option or that process has been showed. So neglecting the thermal load. Okay, in this case we have a stress result over here, which is towards only forces, and all other things come into picture. Value that is applied. Okay, 6672, 6672. Used for neutralizing the stress. There is also one more analysis done for static pressure. Okay, that might be coming internal, and it could be constant pressure that is inside the body. Frankly, it's complex here. I would have having it easy, but that's okay. I think you can understand. So in what we are understanding two big concepts. One is fatigue, and as well to include dead loads in a fatigue analysis. Do you have understood now? Variable amplitude loads, project description. Fine. So majority of the solving happens in these different studies, static, thermal, etc. When it comes to fatigue, frankly, is nothing much. It is just simple that are happening. More of post processing that is happening. Sorry, PDF. Okay. Here it is. Looks okay. Yeah, we will see this in the software how to add. Should be all done. Fantastic. Okay. So we have these different studies solved and ready. Certain have pressures, etc. But the way they have been accounted in a fatigue analysis is important. So the select fatigue. We have now other options like before had only variable amplitude and constant amplitude. We also have the harmonic fatigue or sinusoidal fatigue, and also have the random analysis. These are new features. These are present in simulation premium only, whereas this fatigue analysis, constant amplitude thing, is in the simulation standard as well. So we study. Okay, it goes on as it is. You select a kind of event here, apply the appropriate loadings on it. We get this particular material feature as well. Right click, go there, the material property is selected. I would be using the existing study so that I can explain the things as they are given in the training material. First of all, they have intelligently selected the material here, which is 75T6. This material is actually, if you observe the in front of the name of the material, which is called as SN, and it is more of depicting SN curve over here. Now, you observe fatigue SN curve. There are people putting or seeing this curve. So the way it looks is something like that. Let's leave that stage. This is available by default in the software. Already use a stress of -1, telling it that the timing has been calculated in this way or here. Practical calculations were done at a stress ratio of -1. That is what I'm trying to say. So this is what it is. Now, if you observe, they have taken life all the way from 7,000, that is 318 megapascals. It is almost going to fail at 1,000 cycles to a stress level of 135. Well, almost, if I'm not wrong, it is 4 million cycles. I think about that in one way or other can be considered to be infinite. So remember, if the stress levels are below 135 megapascals, no one doing fatigue analysis. Others and application engineers doing it, they come many questions, but it has no logic or no understanding. So give an appropriate thought on what you're doing, why you're doing, and so if you do not have this curve, if you are not got this from the online content, etc., then always use this option of define from material elastic modulus and based on ASME authentic steel curve or based on ASME carbon steel curve. So these two are the different options which ASME is giving to calculate the curve based on the elastic modulus. So you can actually do that. What it is? Okay. There's a question which says what difference between the R value under defined and the R value in the table data? What do you mean defined? One is this one. So table data is there. Okay. This R value is giving the value at which the practical test has been done. Okay. Second, we define, we can actually manipulate and say even though material curve is of that level, actually the loading is happening in a different way, or we expect it to be happening in this way. So those are considered appropriately. Now back here, yeah. So two different events have been added here. One is thermal stress, okay, which is coming from this particular study. And saying it is a zero-based curve and the loading is 2 million cycles. And thereon we also have one more event which is more for static pressure. So this is a simple analysis we are doing it, and we are loading ratio here. Now this loading ratio is more of what is coming in the square. So set in negative direction. So these two are done, and now you can observe the analysis. Oh, by the way, the definition is this is it. So we define the material. Ideally, if it has it, no big deal, it's all perfect. If it does not, then it is a big task to get the material, or we of course select the ASME option and the software will calculate the material for you. And this is it. So I solve it. So I'm taking static pressure. This is an error that you might experience quite frequently, and the option is we copy the mesh as it is. Sorry, error. Mesh not identical for all the studies and different events. I wish it was identical. I thought it was identical. It should be identical. Suggested method, guys, if you are not aware. So the thermal analysis. Here on we have to copy the same mesh to thermal stress. Okay. Obviously, it will say that it wants to resolve. Doing it in this way, I don't expect it to solve, but I can always try. But process is for analysis, or it is multiple analysis. The way it has been done here, I suggest copy the mesh from one to another instead of recreating the mesh. The only way you can ensure that all studies have the same mesh as that thing. What out of the initial study. So now then I would like to solve this without meshing. Hopefully it does that. You need to jump onto solving. So this is the process. It might take some time to solve. I'll try to trigger them one by one. But meanwhile, I observed that I already overshot 1 hour. It went up to 10:15 now. Let's take a quick break of 5 minutes to 10 minutes. So it is 10:50 now. Let us start back in 10 minutes at 10:25 Singapore time. Okay. Any time around here. is in one way a very involved topic. Um, so I'm sure if I covered all the topics, to stop me, ask me, missed out. If any incorrect explanation, please challenge me so that even I can learn and improve my knowledge. Okay, please feel free to do. Okay, but again has gone back. So as you saw, after it allowed me to solve this fatigue analysis, but it is I don't know what went wrong, but it is taking a bit more time to solve. I would expected it to be very fast, but it is taking more time. Frankly, not the solution time, but something wrong with my setup or the way I triggered the things over here. Take one, I guess, or I am not sure if you guys are aware of this, but typically you are using a online tool like WebEx, what I'm using now, or even GoToMeeting, etc. The graphics capabilities change. That is, the WebEx will take control of your graphics, and it is actually, uh, or if I should say, if it is of a lower level, but it's of a different quality than that required for a CAD platform. So, do unexpected things that might happen when you are actually doing such things online, especially if you are solving or post processing. Pre-processing is fine, which not need too much graphics, but post processing, there are problems, and frankly difficult to troubleshoot because it can at any different level, and difficult to say whether the graphics card problem or these things. But ultimately our observation, two versions, like especially there were even a few no crashes for WebEx when Sol and WebEx was used together, and resolved over a period of time. Typically, when a new version comes, it comes with its own problems, and not only SolidWorks, but even WebEx has done a huge number of improvements in their front end, and that can make it different. What I'm facing now is because of that. You can see it is a kind of image on my screen. These are not buttons, but more of images which are getting stuck around here. So one thing which I can do is I can stop sharing and try to get rid of these things, and then come back to you. Share the screen back to you. Okay. In the meanwhile, guys, any questions on the fatigue analysis? I will not give another break. After this, we'll just start off with the last two chapters of this lesson. So please think, any questions, ask. Okay. Once you start sharing, the web session takes control of your entire thing, and things like that. Okay, 127. Fine. Okay, that's all set. Let me also quickly open lesson. Oops. Prefer 10 directly. It is shop server, yeah. Let me check beat that has been used. I'll solve only that one. Okay. Only tick has been used. Hope it should be fast. User can show you a few results as well. So I'll show you, and later we'll move to drop test. And study more to show you the results, and of course of a variable amplitude. So we are seeing that part of it. Large displacement is happening, and hence they have solved a large distress analysis as well. Okay. Level solves, yeah, one, because there's few good kind in the fatigue analysis, random variation, variable fatigue training. Okay, failure criteria are not the criteria, but the way you want to treat the mean stress, etc. direction. As explanation, you can Goodman is recommended for brittle materials, and of course in terms of stress. So sometimes these are defined by the customer, so appropriately you can use it. But these are available in the software. One of the basic requirements for a fatigue analysis. If people are aware of this and they ask, "Do you have it?" and ensure you can convey this fact. Okay. Next is this one review. This one discussed directly when we were using the software. Detection factor, FK we discussed. Probe damage plot. This should be okay. Damage results discussion. Right direction. I wish it was fast, but it is taking more time. That's okay. Deadwood in fatigue analysis. This is not anything with the software, but this is just a process that we need to understand if dead load comes. It was only a knowledge-based article, but now we have included it in the training manual. I try exploring it. I'm just scrolling to the training manual to check if any other important topic has been left out of the discussion. Okay, we can discuss this question. That's all. Okay, so these kind of bins are when we discussed about variable amplitude fatigue, these are the kind of outputs or inputs which are relevant to us. Called as the rain flow counting method, or many different words are there. Basically, the stress history is decomposed. So they are decomposed into different cycles. So ultimately, when you see that complex, understandable graph, it is really cut into the small constant frequencies, and then those are segregated to understand the amplitudes of different levels. This is packed actually. It is a bit more involved topic. Things are there, but ultimately when it comes to practicality, we end up discussing only life of the component. That's it, or how much life is limited or available in the component. Okay, anything more that remains? Yeah, so this curve can be imported. This is at 31%. Questions? I believe they should be and should tell us if we have understood all these topics. Okay, let me get the chat window open. Okay. Paralysis is compared from stress results obtained in static analysis. The fatigue failure expected there, that is the damage, is it more than equal to 1? Therefore, does not imply the onset of yielding. Interesting. What do you question? What is the answer? Does it the onset of yielding? Now we have understood this topic, that is dam is more than equal to 1. Guys, on to back. Yes. Okay. Then I will just accept it and go ahead with it. No problem. To that. Because component, I'll go to second question. Because component loaded by fluctuating loading typically fail due to interest. Fluctuating loading typically fail. Okay, due to the fatigue is not essential for safe product design. I think this is very easy one. Okay, a GPS navigation system on a traveling vehicle. This product would not be analyzed using fatigue solder simulation. What do you say? Navigation system is mounted on a dashboard on vehicle. So here the pointation or what you want to think is more towards this has to be analyzed for fatigue or vibration. As simple as that. And from what is more, this might be failing more because of vibrations and not fatigue. And is anyone there to challenge me? Iskandar? Okay. So David is saying yes, it would fail. So my logic is very simple. Of navigation system, it would vibrate. So that's my point. This product, we are not worried about fatigue failure, but we might be expecting more of vibration failure. And if constant movement happening, and we know it is going to come, other just sitting around there is no load variation happening. It is more of vibrations that is important. There are a few more things when I challenge you. I think you want to. I am wrong, but yeah, I think I understood the concept. Excellent, thank you. Let's move to question 4. A loading history for the above case would fit the dash event. Okay, is more related to this lesson. Okay, fantastic. So guys, binding of fatigue. I wish this was fast. This is 61%. I can show you the results once they are done, but the moment I'll let it go on its own pace. No worries on that. Okay. In fatigue analysis, I will discuss quickly the results after those out in the analysis. But in meanwhile, I'm going to wait, but I'll move on with the drop test. So, this interesting topic in this is it is active to talk, discuss, and say a lot during demos. But you might face an exam question. You might want to understand this in detail. But from own personal experience, unfortunately, we don't have many customers, only customer who are using this one effectively, and hardly one or two customers who are comfortable with this, and they say, okay, we can accept this result. But I'm starting with a negative note in this. I'm conveying the limits of this module. Okay. First and foremost, this has gone down. Let me get it in the right place. Okay. First and foremost, remember, this is the only module which is actually using explicit time integration to solve the problem. So this is not an implicit solver. This is an explicit solver. Okay. Typically, explicit solvers are designed or are more strong in some cases of large, I would say, deflection. They are like large change in the locations or the movements of the body. This can also cause to large amount of stress in each of the local elements. Okay, this is how it is. So these softwares work with respect to time for those things and can deliver more accurate and faster data for huge deflections. I'm using the word deflection, but I believe you understand what I mean to say. That is what it is. Now, saying that, okay, that is I would say the strength of this module. But that on the flip side, typical such large deflection analysis need nonlinear material. Softwares like LS-DYNA or the Similia explicit analysis, they come those capabilities which huge database as well as capabilities for those nonlinear material, and they are suited for that. So unfortunately, we are limited with that one. Saying you will also observe, even though I am saying it is faster, typically when time comes into picture or the dynamics comes into picture, it takes more. Really, it will take more time to solve. And we always want such bodies to be simplified into shell elements or simpler scenario. And we might want to idealize such geometries into shell or beams, and both these are not supported in drop test. So again, you will be many geometries which need comparatively large number of elements, and start solving them in our module. You might see times as 10, 20 days and 30 days as well, and that it makes no sense of using that module for particular product unless you want to simplify the geometry, make it very simple and get it going. So its own good and bad points. You can use it appropriately, and you can take appropriate decisions. But saying that, I always encourage our VAS and you guys application engineers to move to dynamic analysis that is more robust than this one. Yet it appears to be taking more time than explicit, but I believe that is giving more accurate and realistic results than what we might be getting here. So this is what I would like to highlight. Quick one, anything else from this slide? Typically driven by gravity or initial velocity or the velocity at which it is going to impact. Okay, and it is more talking in terms of equilibrium forces and accept such analysis without damping, but the fact is damping is ignored. Okay, damping is ignored. Only damping comes is because of the stiffness that giving to the floor to which it is hitting. Okay. Yeah. This is more of a balance between inertial forces plus elastic forces, these forces versus gravitational forces and impact forces. Okay. Yes, then we'll see it in the software. I will also show this in the software. Software. Yes. Fine. This is also. Yeah. How my results are going on. Any questions on drop test? Finally, nothing much to discuss. It is a simple analysis. Actually, it needs far more things than what we can do actually. Yeah. And for drop test analysis. Is drop test same concept with dynamic? My answer is yes. It is almost the same concept. Only this in drop test we have a ready-made flow. That is the place this particular object is going to fall. That flow is ready-made available in drop test analysis. That's it. Okay. And, the theory that is used for drop test is a bit different, which is called as explicit analysis. Whereas in case of analysis, we actually continue using the impact analysis. I think it is a bit more of an accept the file anyway. Okay. So, no. Don't say. Don't say. Okay. The file which I had opened has a similar name, and that can create problems. Okay, that's okay. Let me go down, and I think I can discuss the setup here because the solution will take some time. So with them, I might want to keep all these results ready when I teach these lessons. That would be easy. But yeah, in terms of setup, if you are creating a new simulation study, the drop test option is here. You are selecting it and it goes on. Then typical material properties, as mentioned, these are all linear static properties. So nothing, no much control here. Apart from yes, a little plasticity one is there, but this I'm not sure like how much I would accept it, but yes, action is there. But it is there on let's see what it is about. Okay. Yeah. First of all, if you observe, there are no options to get a shell. Yes, shell manager is there, but it is not allowing you to convert these to shells or anything. Okay. In terms of contact, you can see here these there, but obviously okay. By the way, this unlike static, this is dynamic. In sense, this is an explicit code, so you can have this is not using the method of eigenvalue extraction and thereon dynamic analysis. So then actually detect contact between two parts effectively, no doubt on that. And the stiffness of the geometry can change over a period of time. Okay, so in that sense, it can actually simulate those kind of things. So when it comes to setup, so material property creating things is straightforward. But what in terms of setup, the options that we have are all what you see over here. Now, first and foremost, drop height, the total height from which we are going to drop it, or only we can specify the velocity of impact. We are talking of drop height. We can also talk about the location from which we are measuring. So it's either from the centroid, or it can be from the lowest point on the part. Okay, you can decide from where you want to measure. There are gravity. So obviously, if you are specifying the height, you can specify the gravity and the direction of the impact. Okay, that tells it how to fall or where to fall. Target, the ground which it is falling. If it is normal to gravity, you can keep it, or you can select a parallel reference plane and decide to shift the direction of the this is what it is. Fantastic. Damping we are discussing, but remember this is not the material damping, but this is the damping of the wall on which it is hitting. Okay, it's different. So to understand that, as I told you, unlike unlike what in the dynamic analysis, in drop test we don't have, or we do not talk too much on the wall which it is impacting. As dynamic analysis, we are actually we need to create a dummy component and hit a wall on which it is going to hit. Okay. Apart from that, we have this results option. Be a bit or a lot of be sensitive towards what you are giving here. Try to understand first of all this solution time after impact. Once it hits the ground, we are seeing how it is going to move over a period of time once the impact has happened. Okay, and then we also have these things like if you want, you can typically if we save all the things, then this might be huge analysis that gets saved. So we want to do that, and to do only for, how can I say, the if I put integration analysis. So it can happen that for not only seconds, but it can happen, it might end up saving the results for every microsecond. Okay, we are talking about microseconds. Try to see here. So even if I change this from 5 to 10 seconds, the 5 to 10 microseconds, the solution time might show up like crazy. Okay, so, and as well the result files can be huge. You want to decide on after how many iterations you want to say, or you want to have a workflow sensitive sensor, decide the graph points and just you have to see the behavior of the setup after it has hit the ground. Okay, like this guy has finished analysis, hopefully I can solve it. Has ended up with the same message, and I think it has to do with fatigue analysis on my machine. Oops, that message also went on. So I would like to discuss fatigue results, but in the meanwhile, I'll also trigger the drop for at least one analysis. Okay, this is also fast. Okay, so faster than expected. This was, then I'll finish discussion of these results and then we'll go. Okay, that will do. Okay, I come back to this static fatigue. Okay, so material property definition all same, no big difference. Sorry guys, I might be confusing you, but I quickly want to discuss the random loading options that we are using in fatigue analysis. So here we have taken the input from a curve. You can see here when go to editing, you can actually load the results from a curve, select the appropriate options. Actually you can say get curve and import the curve over here. We can give the path where the curve is present and just import it from there. Okay, this path, by the way, can be given in simulation options, SolidWorks options, or at multiple locations, no issues. There on this curve is something as you are seeing here. Let me use the view option. So this is the way it looks. Okay, quantum. So you have such a curve for a fatigue analysis that can be input over here, and the number, it can also happen that this particular curve is repeating multiple number of times. Okay, that is our curve you are having is, so probably instead of inputting this entire curve, I input the curve only up to 500 points. Okay, you can see here we have gone up to 2500, but I input only up to 500 points, and the pattern is almost similar later. So I said this curve is repeating 5, and that's enough. Okay, because it is difficult to have the curve for 2500 points and the time that it takes, etc. So that's the way is. So in terms of input, this is what it is. Previously, we just add a, I'm sorry, I think that I'll skip that. Just added a simple constant fatigue event, whereas here it is a bit different. And even here there are result options, so you can actually do the calculations for the whole model, or just only. Obviously, it will become faster as you time, and matrix chart calculations decide like those rainflow matrix. Do you want? You can decide certain important vertex points where you want to calculate it. Now let me close this. Let's click this. We take chart options and plot mix, min, and what else would be interesting? Let's go down here. Yeah, it is. So you can see points are somewhere here. Let me try to see the maximum stresses as well. They should be again at those similar locations. You can see right around there that is showing. So be the maximum at those locations only that we are seeing here. Okay, and the chart. Now what I think hopefully not going behind. No, it's behind, so something wrong with the plot. Let me try to create it again. For megapascals, let me check if it can give me. Yes, here it is. So this is what it is. Frankly, I am not sure I can explain you through this front end, but I'll be understandable. This is what it is. Load range, the megapascal, the mean stress at that point, the count such number of cycles. Okay. And what is important here? So in terms of theory, in terms of discussion, a huge amount of content that we might discuss. Ultimately, when we plot the results here, it ends up with the typical things of total life consumed, total life available, and rain matrix. I'm not sure how relevant it could be, but you can actually is the way I showed you. That's it. Nothing much wrong there. So here, see, this is done, and this maximum thing that you can see. Of course, in this case, the parts are bonded, so it is the fall, the height from which it is falling is small, and the analysis that is done after it falls is also small. So it was a bit fast. But it take more time than what has happened here. And obviously these may not make much difference. I don't know. Yes, it is nice to see, etc. But the results may not make much relevance to take any decision. So better off would be to create graphs which can help us understand it. Okay. Let me try to create a defined time history plot and a vertex somewhere there. This one, no. I think the vertex is around that length. Okay. Obviously, lens is the most critical part of a camera, so they typically try to plot it there. Let me try to take the default things of stress and try to plot it. Okay, here it is. This gives more relevance or understanding of what could be happening is that animation. Should have selected megapascal, which I like. Edition, and I go to megapascal. Here it is. You can see now at a certain time instant, probably when it is impacting, the time is just about 30 microseconds. This is maximum, that is 110 megapascals. But stress may not compare the stress with yield strength, because the failure criteria for dynamic loading are a bit different, and thereon it goes down. So we do have the other graph over here which can help you understand whether it should be accepted or not. So it could also be velocity, which is interesting. Yeah, uh, isn't, yeah, it is resultant. I would don't think it's huge, but yeah, that tells the story. So in line, maybe it touches and that it goes up. So it is reach peak velocity of almost 3000 millimeters per second, which can help the camera designer understand whether the lens can take such a fall or not. Okay, so different companies, different ways, different criteria required. If we talk about material models, those are the only two things that we saw over there. If the company accepts it, then this should be good enough. But luckily, this is a highly simplified model, so things appear to be faster and good. But I have seen crazy times that the software needs to solve such a drop test analysis. This is what I like to discuss about drop test and fatigue, I would say, and fatigue. Questions, guys. In the meanwhile, scroll through the training manual. Please ask any questions. Good. You see here, there's a discussion of will the model break. This is most important that you want to understand. As I discussed many different things on this topic, I just please go through this text. It's on page 235. Will the model break? This is very important. Um, analysis to see, but what next is the point, and I believe are a good understanding that we need to have. Okay, on this topic, fine. Guys, a few more seconds to you all to think on if you have any questions while in my optimization study and get it going. Please ask. Okay, lens is scary as well as good, but good enough. I assume you all have understood it, so good for me. Let no issues on the next chapter, which or chapters, and one of the biggest talking points for simulation professional is optimization, right? Optimization, which is a very important module. But now you might have understood that modules like optimization uh, for are more of post processing. Analysis happens in those things like static, thermal, or or drop test kind of things. Hmm? Even optimization is actually taking results from static and frequency analysis. So if I show you these examples, we have these things called as static analysis, where internal stress analysis is done, where the part is fixed at certain location and a load is applied at the top over here, and a simple stress analysis is done. You want to optimize on this geometry, reduce the weight, play with etc. Those are done. In the meanwhile, I also want to control the natural frequency of this body. So I have done an analysis wherein at the same we know the natural frequency or the first mode shape of this particular entity, which is around 80 Hz. Okay. How to create a new optimization study? It can be either a new design study and just select checkbox for optimization, or go to new simulation study. You should be able to see the design study option. Okay, let me okay, let me different options down here. Let me make this as big as possible. Okay, the second is a bit cumbersome if the number of variables increases, but really, okay, I would prefer having a slide, and I think I do have a slide on this topic. Okay, here, let me put it a proper format, and let me match it. Okay, here it is. So basically, an optimization study is you observe here will need these three things. One is the variable, the variables that you want to change or play with. Okay, they are called as the variables. They are the constraints. So I can play with the variables, but it will be within a certain amount of constraint, and it can be as simple as the dimensional constraints or what is frequency. So it is a frequency analysis to ensure that the frequency is not near 90 hertz, or it should not go above 90 hertz or below 90 hertz. So all such things, or it could be as simple as the stress levels, the stress levels, and I don't want them to be more, more than say probably 40 megapascal. So that's controlled and understood here. Only what remains is the objective. Why am I doing this analysis? Actually, I want to reduce the overall body. So those could be the kind of objectives. Those need to be given to the software. So that on giving these three things, software will do multiple iterations and come up with final dimensional details of the model, which as per your constraints and as per the dimensional details that we are given. And as ultimately optimization is just an algorithm. It is in one way, it is not any matrix solving or a finite element analysis, but just taking the results from FEA, that is either a static analysis or those kind of analysis, and opting as per your inputs. Discussed variables could be goals could be something like this. These are the different goals that one can have. It could be variables. Now the interesting topic, when we specify variables or when we specify those variables, ensure that we are doing such mistakes wherein on changing the variables the intent itself is lost. Okay, ensure that whatever changes we give are within the design intent of the geometry. And okay, the condition would be, as I told you, those could be the limits that we are putting to do. So those needs to be given, like the bucking, the first tenth bucking load factor should be within certain thing, or the frequency resonance should be below a certain value. Okay, so at a per level, this is what it is. Let's get into this software to see what has been done. So typically static and frequency analysis is done before. Thereon we specify the variables. Now let me get out of this presentation. Where is it? Here it is. So if I want to add a new variable, I just select it over here. I get different options, like I can give the name of the variable, whether this variable is a model dimension or something else. If we are into model dimensions, all are activated here. If not, you can show them appropriately. Give the initial dimension. So initially, this particular model dimension can start with a certain value, or we can directly select here that value is input. The dimensions are already selected. Okay, so those are done here. It can also be other things, like if you have created some global variables, those can be used here. Other simulation data, like I can have data like it could be certain force which I want to play with, certain kind of different quantities. Those directly manipulated over here. So here if I select force, it comes down. I can change the force values, etc. over here. Or it can be the material as well. This was a kind of new feature which came up in 2014 version, wherein we can select the material that I want to have it or compare in this particular analysis. Okay, so those are two different options that can be given as variables over here. All variables can change with the range. They can script values, or they can be with range with the steps for those range. So if range, the minimum value is 50, the maximum is 100, and actually playing within that range of 50 to 100. So a few other different things. Second thing is the constraint. Now constraints can be different things. It can, again, if there is a sensor, typically they come from sensors. So they can be from simulation data, these simulation results that can be used. It could be mass property, dimensions, etc. So any one of these can be taken as the constraints. If I take frequency, the model max, can decide which frequency you want and take that particular value for as a constraint. So I close this and go back here. So now if you see here, one is rest, he's saying it's rest. Yeah, over here in terms of constraint, it's as simple as you just want to monitor. You want to see the variation of that value, and that would be similar to what we saw in design insight. Okay, other things could be monitor only. Sorry, is greater than or is less than or is between. Is greater than, the stress should be always more than probably Pascals, etc. So those can be specified here. Typically, we want a stress to be less than a certain value. Displacement as well you can control. Frequency is between. Here we are using between, where we allow frequency changes between 80 to 150 Hz. Anything would cause damage to us, and above is not acceptable. And what else? Displacement is another thing. Okay, this is what it is. Goal, it is as simple as minimizing the mass. I want to minimize the mass of the entire geometry. That's it. And I am not going to run here because it might take some time, but yeah, we can do it. And said the scenario appears to be only one, but actually when it solves, it does many things, and it does the iterations as shown over here. And these values, now iteration 1, iteration, all these iterations, these values have come automatically based on the algorithm. This is the only difference between design insight and optimization. This is a big difference. In this insight, we are actually specifying what value to be used to give you the results. Or here, software does it for you and get a final value which can be optimal. So in if you observe here, this is the initial dimensional details which is cell started, and it has done a few iterations. It comes up with a final dimensional detail, which it shows optimal. This way the model can be. And if we try to observe a few things closely here, one of the dimensions which was 100 initially, it is proposing a dimension of 63.58519. Obviously, this is not manufacturable. So we can, like first, we can take these dimensions and then round off them to upgrade things. So typically, 63 might change to 65, 248 might change to 250, and those things can be changed appropriately as per practical requirements. And thereon, we might want to do one more analysis to check looks of the dimensions given by you. But this is a good indication for you on different dimensions that one can use to model, and you're concluding on the design without much brain from your end. We are just giving the limits, and software can guide you on that. Let's check mass. How much did it reduce? So it went down from almost 73 kg. Oh, this is a heavy component. 3 kg to 60 kg. So this looks good. This is what it has done. And displacement, it has increased, but it is allowed. It is within the limit. The limit is less 0.5, and we are 0.27. So that's okay. Frequency, you can see the optimal one has a frequency of 80 point something. We had a limit of 80 to 130, if I remember rightly. Yeah. So this what has happened. Only in what I would like to highlight, you might be seeing some in gray, some in pink, etc. So these are like if I put it in a different way, if you see here, there is something called as fast, and you of course it is difficult to say, but all studies, all these iterations not have been solved by the software. Okay, it is some intelligent algorithm. So if one step taking 5 minutes, 10 days will not take 50 minutes. It could be faster, and that is because it is not going to solve the analysis for all the iterations. It is for a few, and it interpolates. It is for the others. Okay, so the way it goes on, and it comes up with a final dimensional details. So the results from these may not be absolutely accurate in terms of stresses and deflections. So to conclude, you might want to go into a local, take those dimensions, and I saw like once you click here, the dimensions are updated. You can just set static analysis. It is really updated here. You can solve it again and get the true stresses and deflections. That is the best way I suggest. And apart, these pink ones are telling, if you see here, current iteration violates one or more constraints. So obviously this is not acceptable. With the constraint, it is highlighting in a bit more different color. These are okay in terms of constraints, but there is more scope for improvement. So that's what is done. To do it in such a fast way or a slower way can be selected in the properties of the study. We can always select high quality, and it might or try to solve for most of the iterations that have been selected here. Document folders include report, use current view, motion instructions. So then this is fine. What is world report is fine. Okay. In terms of results, I can actually create such graphs to see how variation has happened, but obviously the optimum is more relevant for us. And okay. I think okay. What else I can show you here? Okay, this is what I can say about optimization. Please think questions. I'll scroll through as usual through the training manual to check how it is. But any questions, please ask. Anything, guys? User vessel study. In this version, that is 2015 version. Was it 2015 or 2015? I'm confused. But yeah, we introduced this thing called as load case manager. Okay. Many of us had a question which said, is it similar to pressure vessel study? In one or the other, answer is yes. Pressure vessel study also does a combination of results of multiple things, but the way the load case manager handles is very different. And the important application, as per the name of this study, is towards pressure vessel design. And we put it in a very specific way. This is what it's all about. Stress linearization is what it does as per the requirement of ASME boiler and pressure vessel code section blah 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 blah. Okay, so this is what it is, and this is a post-processing option, just like fatigue analysis. So we need to do the other different analysis. Thereon, we can take the results from those studies and do stress linearization. That is it. Next of the way, typically the questions, the problems or the questions that you face is, do we have a customized thing for pressure vessels, or do we do it in a more accurate way, or how can I say, is it customized for pressure vessel industry? Unfortunately, or are you certified from ASME or this kind of things? But our general purpose code, it is not, I would not say it is a customized or a concentrated code. There are more softwares like PVL8, etc., which have ASME code imbibed in them, and after the analysis is done, they directly know whether this boiler is acceptable or not acceptable as per the ASME requirements. But those codes are not using FEA to solve details. They are concentrating only on one thing, and that's stress linearization. Their own ways of calculating linearized stresses, and they directly jump onto that particular localized thing. So this is what our pressure vessel design code is doing. Once we have the linearized stresses, the user has to take his own judgment. It is like any, oops, what did I do? User has to take his own judgment in terms of whether the results are acceptable or not acceptable from the pressure vessel analysis. The ready-made thing, it is like any other stress analysis. What else? Will software. Yes. Okay, and close this. Don't share. Here it is. Let me check first. Optimization is okay. I click this study. I can close it. Okay, cool. All right. Okay, it is only for a single part. No. Trigger. Let me check results. I thought I have given the results. Yes, they are there. Fantastic. This can a lot of time to me. Solving. Let me go to the study. First, this setup. So if you see, typically you are creating a new study, you can select the pressure vessel option and you can create it. At the top here, you are seeing the equation that is getting created, and actually specify the multiplication factor or scaling factor here. I can select the different studies from which the results have to be taken. So typically it will take the stress results from there. I select it, that is multiplied by 2, and if I click the next button, you should be able to see it at the top here. Why didn't it refresh? You would expect it with one pressure further. Let me delete this row and let me just show updating it by a different factor over here. Can't I do that? Okay, one. Okay. Then you can see here it is updated. One, and I take pressure here. This should be good. This is the updates. Okay. So this addition. So in short, we have to multiply the results of each of those individual studies with whatever factor you want. Then we are just adding them, and the addition can be linear combination or SS, which is like square root of sum of squares, something like that. Okay, so it is neutralizing on the negative values and it is going to help add it. Okay, yeah, no multiplication factors, it is directly taking it in this way. Linear combination, we have a bit more control on that fact. Okay, once the analysis is done, cannot should have identity should have. I need to do, I did not check. I think we need to check all the studies, ensure everything is okay. It is as simple as the result may be out of date and they are not updated. These are basically from your version and not able to solve it over here. If it is to be quick, while we discuss this, I think one easy thing which I can try to do is reduce on the number of study that we want to combine here. We do it. Set up, get rid of this, linear combination, only one pressure. Will it at least solve this? If pressure is same, I think only one study should be okay. Let's try. Yes, work. Even though the this is showing this, but actually the big model which is trying to solve. Okay, and let me scroll this. Guys, at the end of simulation professional training manual, please thought any questions on simulation or simulation professional ask. We might end this session in another 5-10 minutes. I think this first. Okay, lineation, as I told you, is square. Okay, not sum, square root sum of squares. Okay, this is what it is. Stress intensity. What the method is. Find things which stress is required, what value is required is all specified in ASME, and this study is more to compare or understand those things. Okay. This normal stress intensity plot, which is the difference between two principal stresses. So this as it is, and yes, this is a full thing. We try to get it. Result. New option that is present and is most relevant in this study is somewhere here. Once you do all the normal analysis, do the low combinations, you know, linearize. Is the only, I would say, this is the only relevant option that is necessary or as per the requirement of the ASME code. I'm getting 2 points at this cross section. I press calculate. It is going to calculate the linearized stresses, that is normal XYZ, shear XYZ. Of course, kept the von Mises and stress intensity as well over here. and variation on that, how can I say, on that, between those two 40 points can be seen somewhere over here. Typically, if you see here, the default stress results are the red line. What 0, 0, membrane stresses are varying. What is this green line? Green line is more moving from a compressor to a tensile load, and the red is the overall thing, and the bending membrane appears almost 0 here. It's fine. So this plotting for those locations across the thing, and for the one is for xz, xy, normal z, normal y, and normal x. Fantastic. Typically do is to take one of these stresses and just compare it as per the requirements of ASME with the limits specified by them for that particular pressure vessel. That's it. So I said what you are seeing on the screen now is what a pressure vessel designer needs. That's it. And the other specialized code directly gets this thing using FEA, and they can actually compare it with ASME code inside the software and whether it is acceptable or not. So we reach only at this stage where we are plotting this, and one has to take these results and do further detailed analysis, further comparison with the ASME results. Saying that obviously with this method we have more advantages in the sense we have the 3D model, we are not recreating anything, we are seeing not only as per ASME code, but he can also play with the other things and get an optimized design, see the other detailed stresses, and he has concluded he can directly save all these things and how can I say, and create drawings or the manufacturing requirement details. So this is what it is. This is what I would like to discuss on Simulink Professional as per training manual, and of course as per what all I thought. Are there any questions on this topic? No, nothing questions as such. So first I would like to thank you. I know it is really hard sitting very remotely and trying to grasp whatever I am saying. Patience and understanding. Do let questions either through emails or in the next 2 to 3 minutes. We will take up motion, which is a completely different topic than what we have discussed as of now. Of course, it is not 3-hour thing, but I pick up only the important things in motion, because concept-wise, it is some things. Once those concepts are understood, then it is no big deal. You can do it on your own, and let's go on with the flow simulation and simulation premium trainings in due course of time. Of course, I might be covering plastics as well. So thanks a lot. Any questions, please ask in the next 2 to 3 minutes, or I'll slowly start closing this session. If you update me on any changes you want in this format, anything more you want, anything that you want me to do in such remotely, which can be of great use to you, please keep us posted, or keep rather. Yeah.